Hello everyone. Thanks for coming to my presentation today. My name is Mariola Ndrio, and the work I'm going to present here is under the advising of Professor Bose. And this presentation is basically going to focus on markets for electricity. So let me start with a little bit of a brief history behind electricity markets. I'm only going to give some key events because the history behind it is really long and complicated. Basically, for a certain period of time, the supply of electricity was at the hands of these vertically integrated monopolies that were in charge not only for the generation, but also for the transmission and the distribution of electricity up to the individual customer. However, a number of events in the early 70s caused this traditional utility model to break down. Now, though the events that I'm listing over there are by no means exhaustive, there are many other reasons why this model broke down, but briefly, so to speak, a combined crisis in two other energy industries, the oil and natural gas, coupled with an oil embargo that happened to the country in 1993, technological stagnation that the electricity industry was facing at the time. Basically, the efficiency of power production was already starting to exhibit diminishing marginal returns, and push from environmentally friendly policies. Basically, regulators started to push at the time the electricity business to move from coal to natural gas. However, that happened at a period where natural gas was scarce, so it wasn't a very good time to push them. So all in all, what happened in the 70s is we got a number of major utilities in the country at the brink of bankruptcy. And the gentleman I'm showing over there, his name was Charles Luke. He was the CEO of Consolidated Edison, the electric utility that supplies New York City. He managed, I think in 1974 to get a major government bailout in order to save his company from bankruptcy. And the press at the time, if you read the headlines, were very pissed because people couldn't understand how a monopoly business that is guaranteed a fixed return on its investment could go bankrupt. And yet it happened. So economists then started arguing that the supply of electricity, just like any other commodity, despite its special characteristics, must be subject to market discipline. Basically, this proposal came within a context of a wave of deregulation that was happening in Western economies. Some of the key events that forever changed the landscape of the electricity industry was the England and Wales privatization in the UK under the government of Margaret Thatcher, which basically served as a model for subsequent deregulations in Australia, New Zealand, Canada, and also the United States. More specifically, in the US, the Federal Energy Regulatory Commission issued the two landmark orders, 888 and 889, which removed any remaining barriers to wholesale competition and basically encouraged the establishment of the so-called ISOs, RTOS, independent system operators or regional transmission organizations, with a purpose to basically operate the transmission grid of the electric power utilities in a manner that is entirely independent of any business interests in the sales and purchases of power by those utilities. And so it happened. These are areas primarily in North America where that correspond to a wholesale organized electricity market. Each different color corresponds to the footprint of operated by an ISO. So we don't have wholesale organized markets everywhere in North America currently. However, this is where we are most of it today. The system operator is not only responsible for administering the wholesale market, they're also responsible to ensure reliability of the bulk power transmission grid. Now, one would ask, what are the principal elements of these markets, of these wholesale markets for electricity? Well, These markets are restricting our focuses in North America because they can have different designs in other parts of the world. They are basically designed around this concept of allocational marginal price, which was introduced in a book that was published by 4 MIT professors called Spot Pricing of Electricity. And basically what this book introduced is the concept that at any particular node or location of the transmission network, the price for electricity must reflect the marginal cost to the system to supply an increment of load at that particular location. And so basically the market design today largely reflects that concept. More specifically, we have a pool-based model with a two-settlement system, one day ahead and a rebalance in real-time market, where basically the system operator in the day ahead tries to match generation offers from suppliers and demand bids from consumers to produce a classical supply-demand equilibrium price at each node of the network, while at the same time, and this is very important, satisfying the engineering constraints of the transmission network. And typically what those constraints by and large represent is the fact that at any two nodes of the network, you can only transmit a finite amount of power. And this is the reason why we see what we call price separation or price differences at different locations of a transmission network. So you can see here in the map, which basically shows contours of LMPs at the Midwest area, at the area which we belong as well. And you can see that at a particular point in time, at the Minnesota hub, the location, the electricity is traded to the wholesale at approximately $27, while at the Illinois hub, it's traded at $154, which is a large price difference. So in order to be able to allow market participants to hedge against these price differences, typically electricity markets, they go hand in hand with hedging instruments such as financial transmission rights or FTRs. Now, all this transformation, they largely happened at the wholesale level. They did not extend at the retail sector, where we still have today regulated rates. Since every end-use residential customer or small commercial consumer, they cannot switch suppliers in real time. So we have basically the old utilities. Now they manage and operate the distribution grid and sell electricity at regulated rates, but they buy it in the wholesale in market prices, which exposes them also to price volatility in the wholesale. So throughout this was a brief journey of the history behind electricity markets. However, throughout this journey, a lot of things changed, posing and continue to pose challenges to the electricity market model. So going back to, if you recall the map that I showed, what we basically have on the transmission grid, a very complex interconnected system, which different parts of the grids are at the heads of different ISOs. While the grids themselves being interconnected through these transmission lines, which we call tie lines, which I show there with the bold color. However, what has happened, one of the most significant trends that we've seen over the recent years is the deepening penetration of intermittent, very low marginal cost renewable generation at different locations of the grid, and this trend is likely to continue. So this change itself requires basically, in order for us to be able to harness this geographically dispersed renewable generation, which is clean and at a low cost, we have to basically ensure a seamless operation of the entire interconnected grid. Like for example, in the United States, many of the renewable capacity is located at the middle of the country, while the load centers are at the coast. So what happens is that at the wholesale level, the power, that clean and low cost power, has to typically cross the jurisdiction areas of multiple ISOs to reach the load center. And one may ask, okay, why is that so important? Well, you will see that under a market environment, it is not that straightforward to schedule those interconnections. That is not that straightforward to schedule efficiently those interconnections and to allow for market, for consumers, no matter where they are located and how far away they are located, to make the most out of this clean and renewable, clean and cheap resource. So we will go in detail into that and see how those schedules are determined today in a market environment, and what are the inefficiencies present, and how we can remedy those inefficiencies. Now, the retail sector is another sector that is undergoing major transformations, which at the heart of these transformations are low voltage residential consumers and small commercial customers, who increasingly hold value for the grid, either as suppliers of generation with rooftop solar and so forth, or as flexible demand. So we are seeing an increased complexity on the low voltage customer side, which basically will create new challenges. And basically the question that we ask is, what kind of mechanism are we going to design at the retail sector of electricity to be able to incentivize these resources that we see at the end of the grid appropriately? So should we design a market similar to that in the wholesale? Should we extend the competition to the retail sector as well? And if we did that, what centralized entity would we have? Would have to come in with some smart optimization capabilities in order to take advantage of these resources. And should we adopt a similar concept like those in wholesale market to have a locational marginal price, or do we need to take into consideration other characteristics of the distribution grids in this case? So these are, in summary, the questions that I'm going to explore throughout this presentation. And I'm going to begin with the first topic, which is coordinated transaction scheduling. Recall that I mentioned about this, I talked about these tilings and how power is scheduled between market to market. The CTS basically is the state of the art today, is a market-based mechanism that allows power to be scheduled, power transactions to flow from one ISO to the other. So tilings are very important, basically, transmission assets. They are capable of basically supplying a large proportion of each area's demand. To put this into numbers, if you look at the interface capacity between New York ISO and ISO New England, they're capable of supplying approximately 10% or 12% of each area's demand. There has been a recent study that was published and basically estimated that the cost of scheduling inefficiently power between markets cost the customers of both areas, approximately $784 million in the period of 2006 and 2010. As I mentioned before, they are very critical in order for us to be able to harness the geographically dispersed renewable resources efficiently, and of course to enable the seamless and cost-effective operation of the entire transmission grid. So as I mentioned before, the current practice is coordinated transaction scheduling, which is a purely market-based procedure, and we'll see how that market procedure works. It's been implemented over the last 4 to 3 years, and we're going to see how the market performs and what are the main issues with CTS. Now, one would ask, why would you have a market to do that? Why would you have a market procedure to do that? Why don't you have the two system operators? If we assume, let's say, a simple two-area interconnection, why don't you have the system operators of each area coordinating with each other and basically solve and optimize the dispatch resources in both areas, as the two areas being an entire area? However, we'll see that problem is the problem with this theoretical method is that it basically makes the system operator a market participant itself. It basically runs counter the system operator's financial independence out of any interest in the purchases and sales of power in electricity market. So let's look at it a little bit in more details. If I had a simple two-area interconnection where the two grids are interconnected through a tie-line and there's a price at each side of the interface and there is a power flowing at each moment at the interface, then the theoretical optimum would be that you should schedule that much power between these two areas to the point determined or dictated by the minimization of the aggregate dispatch cost of both areas. So how would you implement that in practice? Basically, each system operator would have to compute these curves, which I'm showing over here. These are called supply stacks curves, and basically what they show is how the LNP at the border node or the trading location with the neighboring market varies with respect to varying amount of flows at the interface with a neighboring market. So basically, if you were to look at what happens when there's a zero schedule, you can see that the price in area B is higher than at the price in area A. And since these two markets trade the same commodity, there's no difference. There's no reason why we shouldn't trade with each other. So we can converge the price spread between us close to zero, basically. That's the economic incentive behind this trade. So that the consumers, the customers in area B benefit from the cheaper generation that is produced in area A. And it makes no sense to produce anywhere we are at the left or the right of that intersection. It's a suboptimal solution, basically. So that is the theoretical idea behind it. So we should trade and schedule until we satisfy the so-called no arbitrage condition that the price spread becomes zero between the two of us. However, like I said before, in order for the system operators to implement this, it is as if they are participating in each other's market. While it is very important to note that the system operators are purely facilitators of trade. They cannot trade with each other. They can only implement the trades and transaction requests that are required, that are imposed to them by the market participants. So, having this in mind, the system operator said, okay, so we should, that price spread that we have between us, there is an economic incentive behind that. We can invite market participants to arbitrage away that price difference. So basically, if you are interested in making money, you don't need to have even a generation resource or anything. You can be purely a financial entity, and you can say that I speculate that the price in area A will be lower than the price in area B, so I'm going to buy in A and sell high in B and get the price difference. And the economic rationale is as many bidders come in the market and do this, eventually your price spread will get to zero. That is the idea behind CTS, and the way it is computed is basically market participants are invited to submit transaction requests that leave one area and enter the other area, and those requests are stacked to create basically their own supply curve, which is subtracted by the supply stack of one of the two areas, and the optimal schedule is determined at the new intersection of the supply stack of area A, which is the exporting area in this case, with the modified supply stack. In order to understand this a little better, let's look at it as follows. If I were to take the price difference, the difference between the two supply stacks, what I would get is basically the price spread between the two areas and how it varies with the amount of power that flows on the interface. And that is given by this line over here. At the point when it becomes zero is the theoretically optimum schedule, which we call Q-tie optimization. Now, this curve over here is constructed by the interface bids that are submitted in the CTS market by the market participants, and they are stacked, basically starting from the lower price to the higher, to construct their own supply curve. Good. Now, the CTS schedule is nothing else but the intersection of the price spread with the supply stack of the interface bids. Now, 3 years after its implementation, the CTS mechanism continues to yield inefficient schedules, as multiple reports and market monitors have indicated so far. Some of the possible factors is because it uses that proxy bus approximation. I didn't mention before that those supply stacks are computed at a designated trading location in each area, which basically is used as a proxy for trading with any other neighboring market. And that, in fact, doesn't take into account all the network complexities behind it. So one possible reason would be the proxy bus approximation. Another reason could be the bidding behavior of market participants. As I mentioned before, these are purely speculative bidders. The only thing they care is to make profit. They don't care whether they yield an efficient outcome for you or the system operator or the society in general. A second reason could be possible interactions with other markets. I mentioned one of those is the FTR market. We'll see about it a little bit later in detail. The total market liquidity, the price forecast biases, which is the system operator's price forecast bias, which is entirely borne by market participants, because this basically curves are constructed a certain amount of time before the real price spread has been realized. So whatever error the system operators make here is entirely borne by those guys over here. And last, the transaction fees that the system operators typically levy on a per megawatt hour cleared basis. So in this talk, I'm going to focus only on the four last. The first one has been tackled in an earlier work. So basically, the way I'm going to start by understanding a little bit the bidding behavior of these market participants. And I'm going to do that by recasting the CTS problem as that of a group of suppliers. CTS participants basically could be viewed as a group of suppliers that are competing for flow on a transmission line. They compete for flow over a transmission line, and that transmission line is described by an elastic inverse demand function, which in my case is going to be the price spread function. So I'm going to use the price spread as a demand curve, and I'm going to view CTS participants as suppliers that compete to shrink that price spread, basically. So now there is a question, like, how do you model these virtual bidders, because these are entities that do not have any generation, and therefore they do not have any generation costs associated with them. They're purely speculators. The way I'm going to do here, I'm going to adopt a scalar parameterized interface bid structure, which is basically inspired by earlier work that has been done to study greedy users in communication networks. And it has a number of useful and interesting properties. But in our case, basically, I'm going to assume the following, that every CTS participant I provides to the system operator a scalar quantity, theta I, with the understanding that she is willing to transport a certain amount, xi, which varies with the price spread as shown in the diagram over there. So basically, every participant is willing to accept a minimum price spread, which is theta I over vi, and that price spread increases the more the quantity approaches this limiting value bi. So you can see that I've plotted over there my transport offer and the one that is used in practice. And you can see that the one that I use is a smooth approximation of the one that is used in practice. Basically, the beauty with these supply offers is that they can endogenize the budget information about these virtual bidders. I don't need to worry about costs. Their budget information can be essentially encoded here in this parameter beta I that basically represent the liquidity that every participant I has. And is also a model that allows me far more flexibility in order to indicate what I want to do and what prices and quantities I want to bid compared to the simple one price, one quantity pair. Okay, so we need to introduce some mathematical formulation in order to study this problem more rigorously. I am not going to make any further assumptions so far about the price spread function, other than the fact that I'm going to assume it's differentiable and concave and strictly decreasing in the quantity that flows on the interface. So the more power flows from the lower to higher price area, the more you shrink the price spread, and there is some positive price spread whenever nothing is scheduled between the two areas. So given that, then the tie optimization schedule is very simple to basically deduce by solving this simple optimization problem. Basically, the efficient schedule is where the price spread becomes zero. We're going to use this solution as the benchmark to our CTS outcome. Now I'm going to assume that I have n CTS participants, and I'm going to denote by xi star the CTS flow allocation to participant I. Then in order to determine the CTS flow allocation for each participant, the system operator, given a liquidity vector B and an action bidding vector theta, then the CTS flow allocation is given by that formulation, which basically seeks to find the intersection between the supply stack, the interface bids of market participants, and the price spread. And the CTS schedule is nothing else but the sum of all of each individual flow allocation. So we can do a little bit further analysis. In this market, every participant is going to be paid at the same price, which is the price spread at the CTS schedule. And we need to distinguish between a market that has liquidity shortfall and a market that has liquidity surplus. In the case when the CTS market is illiquid, that means that the total budget of the player is strictly less than the maximum inter-area demand. Then the CTS flow allocation is going to be given by this expression. And the CTS schedule is simply the sum of the CTS of the flow allocations. In the case where the CTS market is liquid, that means that the total budgets of the players are sufficient to supply the maximum inter-area demand, or my ideal theoretical schedule. Then in this case, I would have to be a little bit more careful. The price spread can become zero in this case, and making my supply offer, my transport offer not well defined. So I need to ensure that I adopt the following convention so that my transport offer is well defined for every action and every price that might be realized at that action. And here I describe the CTS market for when the market is liquid. You can see that in the case where the market is liquid, the CTS schedule can yield the optimum, theoretical optimum, provided that all players bid zero, basically bid a zero action. However, the question here is whether profit maximizing participants will ever bid a zero, an all zero action. In order to understand that, we need to use some game theoretic tools, because remember, we are interested in the strategic interactions of these participants. We don't care what happens when they are pure price takers, but rather we want to focus on what happens when these individuals anticipate the market outcome and endogenize that in their decision-making process. So if I were to model the CTS market as a game, I would have to consider the n participants. Each of them has an action space, which is the positive, non-negative real numbers. And their payoff in the case is given by, in the most general form, is given by this equation, which basically you can do the substitution and derive it. The only thing I want to mention is that there is a cost component, where that cost component comes from the transaction costs that are allocated on a per megawatt hour basis. This happens between the CTS market in New York ISO and PJM. So I'm not going to get rid of that term for the time being. And I'm going to get rid of that. I'm not going to get rid of that later. And what I'm interested to basically understand is what will be the market outcome at the equilibrium of this game, at the Nash equilibrium more specifically, which basically an offer profile constitutes a Nash equilibrium whenever there is no incentive for a unilateral deviation from that action profile. So remember that I have not specified my price spread function. I haven't said anything more about it than just those nice properties. However, it is possible that we can guarantee existence of a Nash equilibrium for a family of price spread functions that satisfy that criterion. Moreover, we can show that in the case where the CTS market is liquid, then any Nash bid profile will have strictly positive sum of components, which basically means that the efficient outcome cannot occur in the presence of costs. Remember that the efficient outcome would happen when all players beat a 0 theta. That is not going to be the case. Now, in order to be able to say more concrete, to make more concrete statements, I have to specify some form of my price spread function. Well, one idea, I'm going to restrict my attention to affine price spread, which are given by that form. Those price spreads can occur if you assume that the economic dispatch, which is a parametric optimization, using as a parameter the amount of power that flows at the interface. If you assume that that has quadratic generation costs, then you are going to have the Lagrange multipliers be piecewise affine functions of the parameter Q. However, if you are more interested to see whether there is some empirical evidence that can justify that linear model, you can look at the, if you take the price information from the New York ISO and ISO New England proxy bus LMPs for 2018, and if you run a linear regression between the price of New York and the export quantity, then you can find an R square approximately 0.38. Now, one may ask, is that good enough? Is that good enough? Well, we could do better. However, you need to keep in mind that LMPs are very noisy data. It's highly optimistic to expect that only one variable will be able to explain the most of its variations. So the fact that Q is able to explain approximately 40% of it is good enough. Alternatively, you can run a multiple linear regression between the New England price and the New York price and the import-export quantity, and you can find that the coefficient W1 is approximately 1, and the adjusted R square is 91.2. So there is some good empirical evidence that we can move on with this model. So having this idea, adopting the assumption that we have an affine price spread, and if we get rid of the transaction costs, then the payoff of each player becomes simply a revenue maximization problem. And if we define the social welfare at the CTS schedule over the ratio between the two social welfares at the CTS schedule and the time optimization schedule, then we can solve the game, and we can find that there exists a Nash equilibrium in this game, of course, and then the CTS flow allocation at the Nash is given by this expression. Moreover, if the market is sufficiently liquid, the worst case losses, the price of anarchy for this game is going to be 3/4. Otherwise, the price of anarchy can be arbitrarily low depending on what's the total liquidity in the market. So basically what this result shows is that if you have a market that is liquid enough, then your market-based scheme is going to yield at worst 25% efficiency losses compared to your ideal theoretical optimum. Otherwise, if the market is not liquid and these traders, either you don't have enough traders or financial players, or they have very low budgets, then the schedule can be arbitrarily inefficient. And we can compute the CTS in this case, and as I promised, they can indeed yield the efficient outcome provided you have more than enough liquidity in the market. And if you remove, of course, the burden of transaction costs. Otherwise, when players are faced with transaction costs, obviously they're not going to be the 0 price spread. And here are some, maybe not, but here are some observations. I'm going to skip them for the time being. Now, if we were to investigate this market under the assumption, we had throughout the assumption that everybody knows everything, everybody knows what the realized price spread will look like and what's its function and so forth. However, let us assume that I have n bidders, and then each of them, there is a forecast, basically conjectured price spread by the system operator, and there is a true price spread, and each CTS participant has their own conjectured price spread. Then in this case, if I were not to ignore the transaction cost, then I would have a game where the payoffs of the players look like this, fairly complicated form and very brutal to solve in the action space. However, you can solve it and you can compute the CTS schedule in this case. What basically this result shows is that, first of all, the system operator, as expected, will never schedule anything above the style optimization schedule. Always CTS, remember, is going to be to the left of tie optimization. In that case, whenever the tie optimization schedule is higher, whenever the true real optimal is higher than the tie optimization, then CTS simply exacerbates the performance. They realized that if we had a CTS crowd with homogeneous beliefs, then the realized price spread would constitute of two components. One of them is, as I said, entirely dependent on the system operator's forecast, and the other part will vanish as the crowd, the number of participants grows large. So even if I were to inject more and more competition and I were to set the transaction fees to zero, still in this case the market participants would have to bear the forecast error of the system operator. If we look, it's interesting to look at the impacts of the transaction cost in actual markets. Here what I'm plotting is a time series of the CTS market between New York ISO and ISO New England, which has almost negligible transaction cost. And this is the price spread time series for the CTS market between New York ISO and PJM, which has basically cost between 4 to 8 megawatt hours. And you can see how this is much, much closer to zero most of the time. This is more volatile, and it's approximately 3.3 megawatt hours on average larger than the one at the left. And the last thing that I'm going to investigate is basically how this market interacts with, how this market may interact with financial transmission rights. Basically, an FTR is a financial instrument which is defined by a triplet. Which represents the source, the sink, and the megawatt position, and they reimburse the holder of the FTR the LMP difference between the sink and the source location, provided that the congestion is from the source to the sink. So very quickly, in this case, if I were to assume that I have a CTS participant, which plays, of course, in the CTS market, but has a portfolio of FTRs that sink in the importing region's trading location, then I could rewrite the payoff and I can construct the CTS gain with modified payoffs to incorporate also the payoff that comes from the FTR portfolios. And in this case, what you would expect is that if the optimal direction is, let's say, from A to B, then participants that have FTRs that sink here, they have every incentive to schedule as less Q as possible in order to keep the price here as high as possible. Because the more cheap power comes from this area, it drops this price, affecting their FTR payments. And that's basically what we show here in our last proposition. However, what I have discussed, what I've analyzed so far is only through this concept of a Nash equilibrium. In reality, players do not have the information in order to make those decisions in the way that I have constructed it so far. What happens is that most of the time players will simply interact with the market and try to find what is their optimal strategy with repeated interactions. What I'm plotting over here is again within the affine model, and with simple update rules on the action theta, you can verify some of the outcomes of the Nash equilibrium. That indeed the high liquidity yields closer to zero price spread and closer to efficient schedules, CTS schedule. Otherwise, we would get very bad behavior when the liquidity in the market is low. I'm not going to discuss this trading project exercise. This is basically market participants trying to predict the price spread between the markets. Basically, this is trying to predict the price spread using 2018 historical data between New York ISO and ISO New England, and using 2019 data in order to test your trading strategies. So if you, let's say you train 24 predictors, one for each hour of the day, for each location, the Rollstone or the Sandy Pond, these are the two proxy buses that they use in this market, then you can see that the player, if it starts with a budget of 250K, it can have a net cumulative profit by the end of the year of approximately 4 million, and 4 million in this one, that's a 2 million. If you put in transaction costs, you can see that the payoffs of the players get distorted significantly. And this is something that everybody, every market monitor has emphasized, that this needs to go away. I'm not going to spend more time in this due to time constraints. Now, what I discussed so far was the first part of the challenges that I remember I talked about, how we need to make sure that the power that flows from market to market is scheduled efficiently. Now let's go back a little bit to this part of the market. As I said, we see an increased complexity on this side of the market, where participants now can be either suppliers or consumers. So if we were to incentivize these people to offer their resources to the grid, could we have, let's say, a market platform where these players provide some private information and some central entity basically decide what would be the optimal dispatch for these resources. So within this context, what I'm going to investigate, what is the right participation mechanism? What is the right structure of a bid or a supply offer that participants of the retail sector should have? And in order to do this, I'm going to assume that I have a market with consumers and end suppliers. Every consumer is described by a utility function, which basically every consumer receives utility UI for consuming a certain amount DI, and every supplier incurs a cost CI for producing quantity SI. There is a minimum amount of inelastic demand that every consumer has. You can set it to 0, this is not a big deal. And there's a maximum supply capacity that every firm has in this market. The only assumption that I'm going to impose is that the utilities are concave and strictly increasing, and the costs are convex and strictly increasing. Now, if I had a benevolent social planner that would have to basically determine what is the optimal allocation of this market, how much each producer should produce and how much each consumer should consume, then they would have to solve basically this problem, maximize society's welfare, subject to the fact that the total demand must equal supply and the constraints, the individual constraints. I'm going to call any solution to this problem as efficient. However, the problem is that these UIs and CIs are generally not available information to the market manager. So how do you incentivize participants? How do you construct such a market? What kind of information should these participants provide to the market manager in order to be able to reach to this outcome, if you could reach to that outcome? So that's the question that I'm going to answer, and I'm going to restrict my attention to a family of functions, which I use them as transport offers, studying CTS participants in wholesale electricity, and I'm going to use them as supply offers and demand bids in a market, in a more general market model, but consumers are also actively participating, not only the supply side. And I'm going to assume that every consumer expresses their willingness to buy through this map. The action of the consumer is this variable, and the supplier uses this map in order to express to the central entity the amount they're willing to supply, and with their action being this. Their decision being that. The market mechanism proceeds as follows. Everybody from the market, whether be it a consumer or a supplier, will submit to the central entity this action variable theta. The market manager then, collecting all this information, is going to determine a positive price such that the total supply equals the total demand. And you can compute that price to be given by this function. And we adopt the usual convention in order to make our offer and bid well defined everywhere. And basically, I am running out of time, so I'm going to skip some parts. If I were to the key idea that I want you to take out of this is that if I were to construct a market that is perfectly competitive, an idealized situation where nobody has any incentive to gain the market or anything, then every consumer would have to maximize this payoff given a market price mu by the central entity, and every firm would have to maximize this payoff. And what we can find is that if the the cost and the utilities satisfy the assumptions that I made, then there exists the competitive market equilibrium at which every consumer maximizes their payoff, every supplier maximizes their payoff, but most importantly, there is every vector SI star that it is defined by this map at the optimal action of each participant, and every demand vector that is defined by this map at the optimal action of each consumer is basically a solution to the problem that a benevolent social planner might solve. This basically, and I'm going to leave you here with a nice story, this establishes the first fundamental theorem of welfare economics. This theorem was proven at different steps, at different times in history by different economists. Basically, Pareto and Walras, they started studying perfect competition by solving these problems, by maximizing the payoffs of each consumer and each supplier. And they came out to find what would be the market outcome in that situation. Now, a more social, Lang, who was an economist that liked socialist policies more, he, a couple of years later, he said, why are we looking at this thing? Why don't we solve this problem? Let's assume that you have a benevolent social planner that has all the information about the system. Then the market allocation should be simply the solution of this problem. And what Lang came to find, it was basically striking. He came to find exactly the same solution that Pareto and Walras had found. That's how the first fundamental theorem of welfare economics was established. What it basically says is very critical. It says that there is a striking correspondence between the outcome of a perfectly competitive, idealized market with the outcome of a problem that is solved by an ideal, benevolent social planner, if that planner has all the information available. That's basically these economists came at the same result independently, and it's very interesting. Of course, they didn't do it with my scalar parameterized supply offers. That's my result. They did it with simply quantity competition for consumers and suppliers. This, and my last statement is going to be that these parameterized offers are not only useful because they do yield that competitive outcome, they are also very useful because you can see that even when the players want to be strategic and gain the market, then the efficiency losses are bounded. Like even in the worst case, when market participants were willing to exercise market power, then the efficiency losses with this mechanism are going to be bounded. That is the two nicest properties of this mechanism. I don't have time for the rest, I'm sorry. Any questions?
So
Yes.
I guess, where are we lacking? You said that we're losing lots of money because we're not getting to these optimal solutions. Do we not have enough people playing? Do they, where's our market not matching these ideal situations?
It's not matching it. One reason, as I said, was transaction costs, which nobody understands why the system operator imposes them. You should not impose them. Otherwise, you're not going to converge the price spread where you want it to be. Second is the trading volume. If market participants, for example, experience, in conjunction with the forecasting error, if the market participant experience that the system operator has an error in its forecast, which yields losses to the participant, then they will probably move away from the market and maybe not participate again or something like that. There's also, I think that another reason with the electricity market is because that when people that have done mistakes or have tried to manipulate them, they face like major fines throughout the years, which this encourages major players to come in with all their liquidity. One such example is JP Morgan Chase, which had to settle for a 400 million fine which is the largest I've ever heard of in electricity markets for manipulating some power transactions. And I think that after that, they stayed out of this market. I don't know whether they're back already. So it's a weird type of construction with a lot of, you need to be careful, and there are fines waiting for you around the corner if you do something that FERC or some other monitoring agency finds to be illegal. However, I would say that the number one thing would be if the price spread. I mean, I showed you what the price spread is between New York ISO and it's like $4 per megawatt hour. That is getting closer and closer. Like the closer it gets, then there's no incentive anymore. You see what I'm saying, to play in that market. So most of the arbitrage opportunity is gone. However, removing transaction costs, like those are like tariffs on trade. Removing those and making easier the processes, the clearing process, and allowing market participants not to have very, very complicated bid structures, I think that would help. Yes?
To build on that though, where do those transaction costs go?
To the ISO.
But they're not supposed to be making money off of it.
They charge though some transaction fees. They charge. But they have employees to pay, right? They have offices, so they charge some fees. They're not there. They should not charge, or charge a very small amount. That's like New York ISO and ISO basically have almost negligible transaction fees.
So you said that in the beginning you can just have each ISO with a supply stack curve because it's like they're playing the other's market.
Yes.
But if this curve is just computed based on the supplies,
it is computed.
The offers that they receive.
It is computed, but nobody of these people is computed based on the offers inside each area. But nobody of these people put an offer to transact with the other area.
Yeah.
It's just their bid information from the internal resources. But nobody of them asked to trade with the other area.
But can we argue that if the ISO has established a way to build this curve and say, I don't have any control over it, it's just based on...
It is purely based on market data.
So,
that's true.
So if there's no action, why there's no planning?
What do you mean if there's no action?
You're not doing it's not like distribution optimization, you're going back and forth, right? So you're not really taking a stake in the market.
What you're doing is you're sending that supply stack to your neighboring ISO, and they find the intersection point, and then they schedule that. However, why are you the entity? Who authorized you to make that trade with a?
So there are two ways to see.
You see?
One is any explanation given as to saying that yes, it is why can't you just say that yes, the market processes, this is the way you clear it, and hence take it or leave it? Perhaps can be gone through, but it hasn't happened. Or perhaps one of the reasons is that, and second is there used to be a market back in the day, which is purely market driven. System operators have nothing to do with it. If you do that, then it was obvious that it was highly inefficient. So they wanted to move away from the purely market based to something that is purely system operator based, but purely system operator based did not fly at all, right? Because literally stakeholders said no. So then they went back and said, well, let's come up with some compromise. So historically, that is one of the reasons, and the reason that was given to an extent was that it is that one system operator assumes position in the other. The other way to think about it, to defend the position that Mariola took, assume that something happens, one area is unable to sell the power to the other area. Who is liable? In a market framework, it is a matter of who takes the liability.
Yes.
In the case of a market participant, suppose you're a generator and you cannot generate, you face $1 million fines. Who is going to take that responsibility?
Yeah.
So it doesn't go to any market participant because they've never said that I want to transport this to the other area. Exactly. So somebody has to be liable for that.
Correct.
Power.
Yeah.
Who is that?
Well, in this case,
System
it's
operator
just these virtual bidders.
System operator cannot. Consumers will pay, but ultimately, it will trickle down to you and me paying. That always happens. but who takes the legal responsibility of supplying that power? Somebody has to, and system operator cannot take it because they are not allowed to take a financial position in any market whatsoever, even if it is another power system's market. So there are two ways to think about it. But yes, I also had this question for a long time. Why can't they just say that this is the process? But historical reasons have stopped.
That sounds like some incredible trickle down. Really, costs trickle down to consumers, great. I had a question, are there problems or risks associated with doing this sort of thing? Like, I don't know, I heard of in the stock exchange, people buying and selling really fast to try to gain little tiny fluctuations and extracting money that way or something, I don't know. Are there
The
problems?
difference here is that you have something clearing the market, so
Okay.
you cannot make infinite trades.
Mhm.
With the stock market, you have market makers, so people who sit behind and basically allow these transactions to happen near instantaneously. So when you bid in the stock market,
Mhm.
It doesn't go to a guy who clears this market. It's going to go to these big name guys, typically partners in hedge funds, who basically take your transaction and say, I accept it. They don't even look at it. They don't care what it says. They just take it, they accept it. And the transaction costs in that case actually go to paying these market makers. So you pay a slight transaction fee, which goes to the SEC, and the SEC will pay these guys to say, like, thank you for making the market happen. Otherwise, consumers like us really can't bid in the market. These big name guys.
To be a little clear, SEC does not take any money.
Who takes the money then? I don't understand that.
So there are two parts here. You pay a brokerage fee. You do not represent at all in a stock market. You don't play. A licensed broker can play on your behalf, and they take a certain amount of fees. They also have some transactions with the stock exchange where you have. So New York Stock Exchange gets
Exchange is the one.
yeah, stock exchange gets for that.
And so the structure of the ISO prevents that sort of.
ISO is a
But
completely
also
just a platform.
The timescales are also very different, like this market clears every 15 minutes, like you cannot go at those very, very tiny timescales here. You need some time in
So
order
it's
to get them.
basically, it's not a risk in this, the way it's structured.
They have people who have proposed this, like this kind of idea for electricity market.
There are two kinds of risks. The one that you are talking about perhaps is less existent. What exists, though, it's kind of very interesting. She alluded to it. There are multiple different financial instruments, right? Some derive their prices based on what prices of electricity happen due to the clearing process. Great. If you put some bids in and offers, that changes that price. So if you hold simultaneously two positions in electricity derivative and one that can actually change the price itself, then you can manipulate it. And that's the example that she gave through financial transmission rights and this coordinated transactions getting you can. And there are examples where FTR positions with another kind of virtual bidding which exists, which is just called convergence bidding or virtual bidding in electricity markets. It's not inter-area, it's within an area, between day-ahead and real-time markets. There, people have published papers on this can happen. And I have been told, I have never verified this, that it has happened. But I have never verified the veracity of the statement. So, long story short, if you have financial instruments that are pure derivatives, one which affect prices, then these two holding simultaneously positions in both can lead to market manipulation. But FERC will go after you.
Exactly.
I'll be sure not to do it.
Believe me.
That's up to you and your moral code.
It's not, they're not
It's
only
a
after,
semi-free country, so I'm not going to dictate.
they're not only after the firms, they are even after individual traders have faced it, yeah, so.
When I was at Cornell, there was this guy who came to give a talk from one of these companies who does tradings. And he and his firm were under active investigation by FERC for some manipulations. There are weird kind of manipulations happen here. So for example, FTRs. In power systems, losses happen. The way the FTRs are structured, they don't account for these losses. So they pay an extra premium because actually real power never went there because it got lost in the network, so they pay an extra premium. So these guys were putting in bids of the following nature. I will get money for price difference between A and B, let's say, like a huge number, 32 gigawatts, and then put another bid from B to A, 32 gigawatts. What happens? The actual money transaction, which is based on the price difference, it gets zeroed out. They bag the premium due to loss that was being paid by the ISO, and that they were making $6-7 million a week. Mark was like, that's not okay. They should have been a little less greedy. Then it would have been good. But it's an art.
Cheating.
I'm not condoning it, I'm saying it is an art, but FERC is also equally intelligent. Alright, we hope. They've been good at it actually.